So here we go, counting in binary. You just turn this into 1, 2, 3, because both bits there are on, 4, 5, 6, going well so far, 7, 8, yeah, I'm doing it, 9, 10, 11, yep, 12, ooh, get a bit stuck there, 13, 14, 15, and watch what happens when I get to 16. That's it. Brilliant, thank you.
Hello everyone, welcome back to your own channel Capsulated Breakthrough. As you all know, my name is Syed Irfan. I am pursuing my electronics and communication in third semester in Sri Venkateswara College of Engineering near Vidyanagar Cross Airport Road. So we are back again today with another new topic, with another new subject, with another new interesting learning process. Yes, it is dsdv, which is Digital System Design Using Verilog. And what are we going to do today? Today, we're actually learning and understanding the concepts, the working, and the whole scene behind what a two-bit comparator is. So, what do we understand by a two-bit comparator? Let us start with what and all we have in today's presentation, in today's video. Starting with the introduction, which tells us about what a comparator is, and next, understanding the binary numbers. So, we have to understand what binary numbers are, what binary numbers do, and what is the role which binary number plays in a comparator, because binary numbers is the most fundamental thing in a comparator, in a computer, because your computers, if there are no binary numbers, your computer will be a zero, and zero and ones are actually the binary numbers. So we'll be learning what binary numbers are, and then working off a two-bit comparator, then the truth table, which will explain. Truth table tells us how the comparator actually works with the help of the binary numbers, and then the application of the comparator. That is what we'll be covering in today's video. So stay tuned. Let us start our video in this. Okay, so what is a comparator? The most basic question to solve in today's video is what a comparator is. So let us start. If you've been following our videos, we always read the paragraph, read what the information tells, and then is when we discuss it. So we'll be following the same steps. What is a comparator? A comparator is a digital circuit that compares two input signals and determines their relationship. Okay, it outputs a specific signal depending on whether one signal is greater than or less than the other or equal to. Think of it as a Let me just move it somewhere else. Okay, think of it as a digital greater than or less than signal. So what does a comparator do? Well, in comparator, we can take this comp word and then we can see that it has something, it talks about comparison, which compares something. That's what a comparator actually does. It compares two of its input. If you've given input A and B, it compares the input and then following it gives us the output. On what basis that it compares the input is what we have to know. So it compares the two input signals and determines relationship. So if we've given two input signals, what does the comparator do? It checks if these two have any relationship. If we've given A and B, where A is 1 and B is 2, for example, A is 1 and B is 0, such like just for example, so it compares the relationship key, is A greater than B, is B greater than A, or both are equal, and then it gives us an output telling ki, yes, this is greater than this, or this is greater than that, or these two are equal. This is what is a basic process. This is what is basic on what a comparator does. Moving on to the next. Okay, yeah. On to the next slide, understanding what binary numbers are. So you can see these one zeros and one binary numbers. To understand binary numbers, we've been learning from a childhood, from grade one, two, three, and then understanding all numbers. We know that natural numbers exist one, two, three. We know whole numbers exist zero, one, two, three. We know integers, negative numbers, positive numbers. We know all irrational numbers, rational numbers, PYQ forms. We know all these numbers. These new binary numbers, where have these come from? So when computer was first built, computer understands only the language of ones and zeros, nothing else. If we are typing my name is Irfan, then my name is Irfan, whole thing will be converted into ones and zeros, and that is when the system gets to know, yes, he is trying to tell my name is Irfan through the binary numbers. So binary numbers is a revolution in the computer industry, in the electronic industry, which has set the development of computers where we are today. So let us understand by reading what binary numbers are. Now, the two-bit comparator, we need and understand binary numbers. In the binary number system, we represent numbers using only two digits, 0 and 1, as I've told you. Each digit positions represents a power of 2. Okay. For instance, in a two-bit binary system, we have four possible combination exactly. I will come back to it, which is 00, 01, 10, 11, which corresponds to decimal numbers 0, 1, 2, and 3. Okay, so what does this tell us? It tells us that the binary number deals with only two inputs, which is 0 or 1. Two digits, 0 or 1, that is locked. We've understood it. Okay, moving on to the next. Then each digit positions represents the power of 2. Okay, so as we have seen in this image, 1 here, the 101 from a right hand units, 1 here is 2 power 0, and 0 here is 2 power 1, and 1 here is 2 power 2. Okay, it goes on increasing. The next digit, if it's 0, it will be 2 power 3, 2 power 4. Keeps on increasing in that sense. Okay, and if we have taken a 2-bit binary system, that means 2-digit binary system, that is 0, 0, 2 inputs, which means you have four possible combinations, which are 00, 01, 10, 11. In 00, the possible values of 0 is 2 power 0 and 2 power 1, which means nothing. Then 0, 1 is 2 power 0, that is 1, the value will be 1. And 10, 0 will be nothing. The value of 1 is 2 power 1, that is 2. So 0, 1 value donates in the 1, and 10 to 2, and 11 will be 3. That is how the system understands binary systems. Okay, moving on to the next. Let's consider binary numbers. Okay, what are two-bit binary numbers? We've taken binary numbers A and B, and let us understand how two-bit binary numbers actually work. Okay, so a digital comparator is a combinational circuit designed to compare two n-bit binary words. Okay, a comparator has three outputs. Wow, how can a comparator has to have three outputs? You can see here, word A and word B are the two inputs given. Then the comparator will be giving us three outputs. That is, if first output states that if A is greater than B or not. Second output tells us if A is equal to B or not. And the third output, which is the one which tells us if A is greater than B or not. In this cases, let's take a look on the truth table of inputs and outputs. Okay, so what does the input say? We have input A1, A0, B1, B0. Okay, and then these are the 4-bit inputs, which are 0, 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, 0, 0, 1, 1, and 0, 1, 0, 0. These are our inputs, and to the outputs we'll have, if A is less than B, we'll get an output 0. And if A equal to B, then output will be 1. And if A greater than B, then 0. 0, 1, 0. And similarly, it will be 1, 0, 0, 1, 0, 0, 1, 0, 0, and 0, 0, 1. Depending upon the input, after comparison only, the comparator gives us an output, which is in this case. Moving on to the next. Okay. Now we have come to the actual topic of today's, that is what is a two-bit comparator. What we've spoke till now, what we've understood till now is all about comparator and binary, so that we can understand how a two-bit comparator works. So let us read what it has to say. The two-bit comparator, unlike the basic comparators, the two-bit comparator compares two sets of the binary numbers. Underline this whole thing. The two-bit comparator compares two sets of the binary numbers instead of an individual bit. Okay. It analyzes each bit pairwise and then it determines the relationship between the two binary numbers. Okay. So what it has to say that unlike other comparators, the two-bit comparator compares two sets of input. That means if you've given two sets of input, it compares all those two sets and gives us the output instead of individual bit. It does not go to an individual bit. It compares the two sets of actual inputs, each pairwise, and it determines the relationship between the binary numbers into them. Okay, here's a simplified diagram of a two-bit comparator circuit consists of AND, OR, and NOT gates. Let us see what diagram. Okay, so this is how, gentlemen, two-bit comparator looks. How many gates have we used? Let us check over again. Okay, we've used AND gate, OR gate, and NOT gate. Let me show you where exactly. Okay, so here we've used, this is the AND gate, this is the OR gate, and these are the NOT gate. So AND gate, so what we've applied four inputs here as a two-bit comparator. Two-bit comparator compares B and NOT A. We send B and NOT A, and that B and NOT A becomes AND. Then these go to OR gate, and then these OR gate performs OR function AND gate, and then again go to OR gate, and we get the input that A is less than B. For A is equal to B, we have to get A less than B, and then we've taken other inputs a segment A naught and B naught. These go in A. Okay, this is B goes on AND directly AND gate. A naught goes to AND gate. So simply again goes to AND gate. These again, and then these again go to AND gates. Go to the OR gate, and we get that A greater than B. If you're not understanding the gates, you have to this diagram. You have to first go check out my previous videos where I've taught you about how gates actually work, how gate representation is done. Because if we speak about the gates in this video, we will extend our 8 minutes of time in this video, and that would seriously deduct my marks. So I can't, I can't take the risk. Okay, so we've got A less than B, A greater than B. When then at after we get, see, okay, so what comparator first does is it checks if A is greater than B. No, then it goes and checks if okay, it checks if A less than B. If it's not, then it checks A greater than B. If not, then it compares these two. It compares these two and checks if this both are not possible, then simply it gives OR gate and NOT gate, and it gives that A is equal to B. Okay, because these two possibilities are not possible. That means the only possibilities left is A is equal to B. Moving on to the next slide. Okay, these are the truth table of the AND operation taking place. If we've given binary inputs B0, then 00 gives 00, 01 gives 01, 10 gives 11, 10. This is AND gate operation. If you know 10, that is 1, and we add 1 and we get carry, and then 11, then 11 gives us 10. Moving on to the next, that is application and the conclusion of today's video. So, in conclusion, the two-bit comparator is a vital component in digital system, enabling efficient comparison of binary numbers. Understanding its operation is crucial for various applications in computers, science, electronics, and beyond. Okay, so what it tells us is that the two-bit operator has a vital component in digital system, and it has numerous various gentlemen. It has numerous and various application in the field of computer science, electronics, and beyond. For example, in searching algorithms, Huffman coding implemented with the help of BSD. They are used in spelling checks. BSD is used in indexing in DBMS. We know that DBMS is hugely popular. And then they are also used in priority encoders and priority queues. So these were applications and the conclusion in today's video. So here we come to the end of today's video. In today's video, shortly we have discussed the top parts, just the briefing part of what a two-bit comparator is, the working of a two-bit comparator, and the deep explanation of the two-bit comparator will be coming out soon after this video. So stay tuned, and until next time, see you.